Swayam Prabha. Digital India. Educated India.
So, this topic is very important for mathematics, for machine learning and artificial intelligence, and is one of the important topics. Call it as a metaheuristic algorithm for optimization problem sharing representation. It comes under the title of combinatorial optimization algorithm. It divided into three parts. One is exact, heuristic, third one is approximation. Exact is based on the branch and bound, backtracking and dynamic programming and so on, whereas heuristic is a nearest neighbor, taboo search, genetic algorithm, and approximation consists of Christoff's algorithm for TSP, double tree algorithm for TSP, and two approximation for vertex cover. So, this is the classification of combinatorial optimization algorithm. Now, all optimization algorithm can be classified into one of three main groups of algorithm: exact, approximation and heuristic. And if I see the previous figure for reference, so the figure is not by means an exhaustive list of algorithm. Instead, it presents some of the most famous algorithm as a typical representation of each algorithm type. So, exact algorithm always guaranteed to find the optimal solution. Branch and bound and cutting planes are some of the exact algorithm one can use to solve integer program. Another example is breadth first search or its improved version of backtracking used in constraint programming. And the downside of using exact algorithm is very poor scalability for solving non-deterministic polynomial hard problems, and they are used only for small instances. So, approximation algorithm try to deal with NP hard problems in a more efficient way in the terms of computation budget. Assuming that P is not equal to NP, a broad class of optimization problems cannot be solved optimally in polynomial time. So, approximation of algorithm or polynomial algorithms that can find an approximate solution while also providing a guarantee regarding the quality of that solution. Usually, the guarantee of such algorithm is expressed as a multiplicative factor, meaning the optimal solution is always guaranteed to be within a multiplicative factor of the produced solution. Sadly, development of an approximation algorithm is a problem, specific and cannot be generalized. So, a famous example is Christoff's algorithm for TSP, which guarantees that its solution will be within a factor of 3/2 of the optimal solution. So, heuristic algorithm seek for high quality solution at a reasonable computational time, but cannot guarantee that a problem will be solved in terms of obtaining the exact solution. So, they can be used as a standalone method, but they are also sometimes used in exact algorithm to provide an upper bound on solution quality. So, some implementation of already mentioned branch and bound use a heuristic to choose which branch to explore the first. There are several ways of heuristic classification regarding the number of candidate solution handled in each step. Heuristics are classified into single solution and population based. Single solution keep only the best candidate solution. In each iteration, the algorithm search through the candidate's neighborhood, then it replaces the candidate with another, often the best solution found. Famous single solution heuristic include variable neighborhood search and iterated local search. Population based, on the other hand, maintain a set of candidate solution and perform search in multiple parts of the solution space. Evolutionary algorithm are the notable representation of population based heuristics. Another property of heuristic is whether it is a constructive or local search. constructive start from an empty solution and append it in every iteration until the complete solution is generated. On the other hand, local search heuristic begins with some random initial solution and then it searches the solution space, making local changes to the previous solution. Next, essential property of any algorithm is whether it is a deterministic or stochastic. Deterministic algorithms follow a rigorous procedure. Their progress and final results are repeatable, meaning they perform precisely the same search in every algorithm run for a given instant and parameters. A classical example of a deterministic heuristic is nearest neighbor algorithm for TSP. On the other hand, stochastic algorithms always have some randomness in them. Evolutionary algorithm are a good example. Evolutionary algorithm represent a broad set of population based optimization approaches. As the name suggests, they take inspiration from biological process like a mutation, recombination and selection. The solution candidates in the population will be different each time the algorithm is executed. Since evolutionary algorithm use the random number generates to stimulate the recombination and mutation, though the final result may be similar or even same, the path to each result are probably different. Another popular stochastic heuristic is simulated annealing, which randomly accept suboptimal candidate to escape local optimum. Now, we have a general purpose optimization paradigms. So, start with integer programming. Hope all of you know about it and recollect and what are all the things related to optimization paradigm. So, probably the most renowned paradigm in combinational optimization is integer programming. It has gained popularity because of the versatility of the integer program formulation and because there are a efficient algorithm that can solve it. If the objective function and constraint of the program are linear, so it is called as integer programming and it can be formulated as a following minimization problem. So, minimum of f of x equal to c transpose x subject to the constraint ax is less than or equal to b, where x belongs to integer, a belongs to r power n cross m, b belongs to r power n and c belongs to r power n. A special case when the all optimization variable x are restricted to the value of eigen value of the restricted to a value of either 0 or 1 is called 0-1 linear programming. Another commonly used terms is mixed integer linear programming, which stands for linear programs that have some optimization variable x real and some are integer. Another practical type of integer programming is integer quadratic program, that is an integer program that has a quadratic objective function, and nonlinear constraint can make the problem much harder. In fact, integer programming with a quadratic constraint is undecidable. In fact, the integer programming with the quadratic constraint is undecidable, that is there cannot exist an algorithm to solve this problem. So, the simplex method is the most commonly used algorithm for solving linear program, that is programs that have a linear constraint and objective function, but the optimization variables are real but not integer. It has an exponential worst case complexity, but amazingly it was shown to coverage in expected polynomial time on various distribution of the random inputs. So, this fact makes it very useful in practice. At first sight, it might seem that dealing with ILPs might be the easier than LPs. Since the set of possible solution is similar, unfortunately the opposite is true. So, integer linear programming or NP hard, but fortunately we can exploit the simplex method to solve integer linear programming faster. So, the relaxation of ILPs is a linear program that has the same objective function and constraint as the original ILP, but the domain of the optimized variable is changed to real number x. Since the possible solution of the original ILP or a subset of its relaxation, it means OPT, optimization of integer linear programs, is less than or equal to optimization of integer programming. Therefore, we can use simplex to find a lower bound of the original ILP. So, the branch and bound is exact deterministic algorithm that utilize a tree data structure for candidate set exploration. The root node represent the whole set of solution. At every iteration, B and B splits into the branches of the solution subsets. So, algorithm solves a relaxation in every node to find the lower bound for the current branch. So, each branch lower bound is checked against the global upper bound, that is GUP. So, if the lower bound is greater than global upper bound, then the whole branch is discarded because it cannot lead to the optimal solution. So, if the optimum of the current node is an integer for all xi in S, is a feasible solution is found and the node is not further branched. So, it is also update GUP if applicable. Next, constraints satisfaction problem. The constraint satisfaction problem, acronym is CSP, is a powerful paradigm for solving combinatorial problems based on constraint. The constraint is a logical relation between one or more variables, each taking a value in a given finite domain. The idea of constraint satisfaction problem is that the user defines a set of constraints and a general purpose constraint satisfaction solver like a CPLEX or G code is used to find the solution that satisfy all of them. Formally, GSP, that is constraint satisfaction problem, is a triple XDC where X is a n dimensional set of discrete variable, D is a set of n finite dimension such that xi in D, and C equal to C1 to Ct is a set of constraint restricted to the valid values of x. So, and the solution of constraint satisfaction problem is a n tuple where A equal to A1, A2 and so on An, where A in Di for which each Cj is satisfied. There are several types of objective one may pursue using constraint satisfaction problem. Example, finding any solution, finding all the solution, finding an optimal solution regarding some objective function. So, the latter of the three is usually referred to as a constraint satisfaction optimization problem. So, the three things are any solution, right, and then all solution and then optimal solution. So, a important type of constraint is so called global constraint. A global constraint is a single constraint that represents a highly structured set of constraints. An example would be an all different constraint that requires a set of variables to take distinct values. It simplifies the problem formulation and it represents a large set of equations, while at the same time solvers can take the advantage of the special structure of the constraint and therefore can be implemented much more efficiently. Now, we are going to discuss the metaheuristic solvers. Metaheurists are a group of very flexible paradigms that can be used to design a heuristic for virtually and combinatorial optimization problem. So, they are a higher level of strategies that combine one or more optimization procedure, typically heuristic but might be expect as well, and other methods capable of escaping from the local optimum trap and performing the robust search of a solution space. So, this flexibility also comes at a cost, researcher usually spend a large amount of time properly designing and tuning their metaheuristic. As observed in many published papers, design and efficient metaheuristic requires a lot of intuition on the part of the metaheuristic designers. Fortunately, there are some solvers that exploits metaheuristic paradigm while preserving various levels of generality. So, one of the most notable metaheuristic solver is local solver. So, it is a commercial software that does not rely on a single optimization approach. It combines several exact and heuristic method dynamically during the computation, similar to integer linear programming solver. So, the local solver search for the feasible or optimal solution, computes the lower bounds and optimality proofs, and can prove the inconsistency of an optimization model. But the local solver not only achieves this on a linear models, but also on higher nonlinear and combinatorial models involving high level expression like a collection of variables, arrays, or even external functions. So, evolutionary algorithm are a set of metaheuristic population based optimization paradigms. There are frameworks that have implemented most popular EAs and evolutionary algorithm, and let us user define new ones such as evolutionary computational framework, that is ECF, and a distribution evolutionary algorithm in Python, evolving objects, and many more. So, these frameworks let us user define a fitness function that is equivalent of objective function in IP and choose a genotype, that is a candidate solution representation. So, this representation is usually either binary vector or real vector or permutation or tree like data structures. Now, we have to transform the fundamental combinatorial optimization. So, another important solution approach is to make use of an efficient problem physics solver by transforming the given optimization problem into the problem that was the solver designed for. This option should be considered before using a general purpose solver. As specified solver will most probably offer better results in terms of computation time and solution quality. For example, flow shop scheduling program is a famous scheduling problem that can be transformed and solved by TSP solver, that is traveling salesman problem. FSSP mean flow shop scheduling problem can be briefly described as a problem of assigning the processing order of n jobs to m missions, where each job consists of m operations. All jobs have the same processing operation order when passing through the mission, but can have a different processing time. So, the order of the job must be the same on each mission. So, the goal of flow shop scheduling problem is to find such a ordering that minimizes the make span. So, that is called it as total processing time. Now, the formulate the flow shop scheduling program as a traveling salesman problem, it is necessary to formulate flow shop scheduling problem using distance matrix. To do the distance can be defined as a processing time of both jobs the following manner. So, the destination d suffix a comma b is a measure of increasing make span of the job B to scheduled after job A, taking into account only jobs A and B. So, another well known example of problem transformation is noon bin transformation, which can be used to model the general traveling salesman problem as a standard traveling salesman problem. So, the methodology is the problem definition is generic problem definition. The proposed solver address the problem that can be defined as follows: given the nodes a equal to 1 to n, where a belongs to integer. So, the lower bound is L1, L2 and so on Ln, and upper bound is U1, U2 and so on UN, and you have to represent the matrix. So, LB stands for lower bound, UB stands for upper bound, all the numbers are belongs to integer of n tuple. So, and minimize the fitness function g of x such that a power m to r. So, m tuple of a domain you take it and it convert into real number. Now, where x stands for x1 to xm and f stands for f1 to fn, and f is a summation j equal to 1 to n of xj equal to aj. So, where fi is lies between li to ui. In other words, given a set of nodes A with the two vectors of upper bound and lower bound LB, find the vector x that minimize the fitness function g while also enforcing the node frequency fi to be between the bound li and ui for every node. Frequency fi is represent the number of nodes ai in the solution x. So, the fitness function g does not need to be the linear or quadratic as in the case when ILP, that is integer linear programming, but instead can be an arbitrary function a power m to r. The vector x can be permutation. So, permutation with repetition, variation, variation with repetition, or virtually any vector of the whole numbers. So, it can also have variable length when least lower bound is not equal to upper bound. Capacitated vehicle routing problem. So, vehicle routing problem, acronym is VRP, is a generalization of travelling salesman problem and was first proposed by George Danzig and John Ramseur in the year of 1959. And formally it can be defined as the definition: you take a graph and the vertex set and the edge set be a given graph, and a vertex set 0 to n minus 1 is a set of nodes, and E is a set of nodes I comma j. If I not equal to j, there is no connection with assigning the weight of CE. Additionally, assume that the available vehicles are based at the depot D in V, and VRP consists of designing a set of routes in such a way that number 1, sum of the routes cost is minimized. Number 2, each customer in V over D is visited exactly once by exactly one vehicle. All vehicles routes start and end in the depot. So, this is the problem, call it as capacitated vehicle routing problem. So, the capacitated vehicle routing problem is VRP with a capacity constraint. In this specific case, every customer I has some quantity demand Qi greater than equal to 0, and every vehicle has a capacity Q is positive. So, to satisfy the constraint, the sum of the demands in each route must be less or equal to the vehicle's capacity assigned to the route. By associating a binary variable xe with each edge E in the graph and assuming that the depot D equal to 0, we obtain the following formulation: minimum summation E in E CE into XE, which is equal to summation E belongs to 0 comma j in E, XE equal to 2k, and summation I comma j belongs to E. If I not equal to j, then the summation of XE equal to 2. Now, 3.11 says that summation of I comma j in edge in XE is greater than or equal to 2bs for all s in V, and cardinality of s is greater than 1. Therefore, b of s equal to summation I in s of qi by q. So, the equation 3.9 and 3.10 are a degree constraint, and equation 11 and 12 enforce the connectivity of the solution, as well as no route has a total demand exceeding the capacity Q. So, the figure 3.1 shows example instance of capacitated vehicle routing problem. So, this is the capacitated vehicle routing problem. Start with the customer, and we have three things. One is quantity demands, another is depot and distance cost, and these are all the route with the help of the edges and vertices, and the distance from one vertex to the another vertex having the activity is mentioned in the distance 67, 68, 12 and so on. If there is no connection, you have to dummy variable, you have to dummy activity you have to mention. So, like that you graph ideas we can denote with the routing of the problem. Next, quadratic assignment problem. Quadratic assignment problem is a famous combinatorial problem that was first introduced by Koopmans and Beckman in the year of 1957, and quadratic assignment problem can be described as a problem of assigning n facilities to n locations with a cost function given by the product of a distance and flow between the facilities. So, the objective is to minimize the cost function. Next, based on the definition, we are given two matrices F equal to Fij, D equal to Dkj belongs to R power m cross n, where Fij is a flow between the facilities I and j, and Dkl is the distance between the locations k and 1. The problem QAP of F comma D can be mathematically formulated as minimum of phi in Sn summation I equal to 1 to n, summation j equal to 1 to n Fij d phi I and d phi j. So, where Sn is a set of all possible permutation phi of the vector, where phi of I represent the assigning of a facility I to the location phi of I. So, here the figure instance of quadratic assignment with the 4 location and facilities. So, this is the 4 location and corresponding 1 maps to 2, 1 1, 1 maps to 1, that is self loop, 1 to 2, 1 to 3, 1 to 4, 2 to 1, 2 to 3, 2 to 4, 2, 3 to 1, 3 to 2, 3 to 3, 3 to 4, like that. We have to have a matrices of 4 rows and 4 column. So, this way we can connect one location to the another location. So, in non-permutation flow shop problem are given a set of m missions m1 to mn and n jobs j1 to jn. We are also given the processing time Pij, which denote how long the mission mi need to process the job j. The goal of NPFS is to find the job ordering for every mission that results in minimal make person, that is C suffix max. Max span is the time at which the last mission m suffix m finishes the last of its job, and the valid non-permutation flow shop problem solution must also satisfy the following condition. Number 1, each mission must process each job without interruption. Number 2, at most one mission can process any job at any given instant. Third, job must finish on mission mi before the start of the processing on mission m suffix I plus 1. Now, we have a definition. So, given a number of mission m and job n and a matrix P equal to Pij, where P belongs to R power m cross n, where Pij is a processing time of the job Jj on mission mi. Let us denote Xij is a starting time of the job, J suffix j on a mission mi is a NPFS, can be mathematically formulated as a MILP. So, minimum of C of suffix max equal to X suffix Mij plus Pmij less than or equal to C of max, where j varies from 1 to n, and Xij plus Pij is less than or equal to, instead of C max is X suffix I plus j, I plus 1 comma j, where I belongs to 1 to m minus 1, j belongs to 1 to n. Now, we have a 16th equation, Xij plus Pij less than or equal to Xij plus m of 1 minus y I j j dash, and he given the condition y I j j dash plus y I j dash j is equal to 1, and Xij is a positive, and y suffix I j j dash belongs to 0 comma 1, where y I j j dash is a binary variable that represent the job jj precede job jj on mission mi. So, this is the figure. You can see the optimal solution of NFPS instance of 6 jobs and 6 mission given by the processing time and computed using the Guropi optimizer, that is so what are all the M1 job corresponding to job 1. So, we have a 1 and 1 to 2, right, 1 to 2 and then 1 to 3, 1 to 4, 1 to 5, 1 to 6 corresponding, we have a what the values and then proceeding in this way for second row, third row, fourth row, fifth row and sixth row. So, corresponding mission 6 to job 6 and we have a entry of these things and we displayed corresponding to the jobs. So, job 1 occupied 1 and job 1 based to the 2 and corresponding is 1. Therefore, this way we have to do for construction of numbers from one job to the one mission to the job 1. So, similarly 2 to 2, 3 to 3, 4 to 4, 5 to 5, 6 to 6 and we have a what all the possibilities of the optimal solution obtained. Next I hope all of you know about the Sudoku. Sudoku is a logic based puzzles designated by Howard Gons. To solve the puzzles, the player must fill in an n cross n matrix, so that each row, column and m cross n submatrix player must fill in so m cross m submatrix contain each integer 1 through n exactly once. So, the most common version of the Sudoku is n equal to 9 and m equal to 3. However, the size m can be any positive integer and n must satisfy the equation n equal to m square. Each instance of Sudoku has some of the matrix fields given, while other are to be filled by the player. So, the number of given fields determines the instance's difficulty. Next definition, a general Sudoku is defined as set of n square fields within bracket grid squares and index set j equal to 1 to n, a collection B of a conjective subset S, example rows, columns and submatrices. Each set B in B consists of exactly n field and initial assignment A equal to Pi Ki with the field Pi in S assigned the index Ki belongs to J. Now, the goal is to assign indices from J to remaining unassigned field from S, so that all the set B contain each index from J exactly once. So, a valid Sudoku instance has only one correct solution. The solution matrix x equal to x suffix pk, where x belongs to r power n square n, can be expressed mathematically as summation of x suffix pk is 1 if p in S, summation p in B x suffix pk is 1 if b in B k in J, then x suffix pi ki equal to 1 where I varies from 1 to r. So, where xpk is the assignment of index k to the field p. So, equation 21 forces each field to hold exactly one index. So, equation 22 ensures that every block contain all the indices, and equation 23 guarantee that initial assignment will hold in a final solution. So, this is the technique we have to use in the Sudoku. Now, the figure 3.4 is example of 9 cross 9 Sudoku is shown. This is the most common n equal to 9, m equal to 3 version of the Sudoku. Nevertheless, this addresses any kind of square Sudoku, that is type of Sudoku where only subset represented by a row, column and square submatrix are allowed. So, let us start with the first row, first column, we have a 9 and then first row, third column we have a 5. So, total we have to calculate. So, in this way we have a form a magic square. So, similarly for the next row, if once we used the number we could not use this, therefore, it will come 8 and then parallelly we have to check in the that is another set is here 2 because we have what 2 cell is a vacant and corresponding the possibilities is 2, 3 and last one is a 7. So, you can use parallelly one pair that is 3 distinct column such that first column and the second column of the entry should be distinct and the third column is also distinct in such a way that we have to design the first row. So, and go to the next we have a 8 and then we have a 5 and then we have a 1 and 2. So, this way we have to go with what second row and third row only possibilities of this cell is 1 and then this possibilities already we filled with all 1, 2, 3, 7, 4, 5 and then only possibilities is 6, 9. So, based on that analysis, so we have to fix the 6, 9 intuitively. Now, the third one similarly the same process we have to fill up 4 and 3. So, this way we can fill up the first set of box, so form the magic. So, proceeding in this way we have what 9 cross 9, 9 rows and 9 column, so that we can fill up with here is 1 and here is with 2, right, and then here we have a 9. So, like that we have to fill up, so that 1 here 2 and 9 will come. Proceeding in this way of the fifth row, we have a 2 9 and then 5 1 3 and then 6 8 4. So, next one is 5 8 6 4 9 7 and 4 is already there, therefore 9 and 7 and then here is 2 we have to fix. Next one is 2 and then 5 4 and then 9 here and then 7 and proceeding in this way for the next rows. So, we can easily fill up the rest of the boxes. So, this is the technique we have to use in the Sudoku. Next, proposed framework design. So, this idea gives an overview of the proposed solver building blocks. It consists of 2 main components, generic solver and a problem specific component. As the name suggests, the generic solvers component is the problem independent part of the solver. It contains 3 classes: instance, solution and generic optimizer. For example, in the figure 3.5, the instance is an abstract class that defines a mandatory properties that every problem instance must be defined. Those are fitness function G, number of nodes A and lower bound LB and upper bound UB of the node, frequency F in the solution. To address a new problem using the proposed solver, a user has to define a new class which inherits from this one. So, it has to set all the mandatory properties and implement the corresponding fitness function G. So, this is the proposed solver class diagram. The problem specific components are Sudoku, QAP, NPFS and CFRP. So, we need the data. The data consists of input, file, problem specific data and configuration, and the functions also required: compute the fitness, load instance, report solution. So, these are all the things important for problem specific component. Now, we have a generic solver component R. It should first of all start with the abstract. So, next to data. Data is based on nodes and then upper bound and lower bound is required, and function we have to compute. So, this is the first step we have to do with the solving the Sudoku. Next, we have to generic optimizer. It is based on instance, solution, configuration and optimization metadata. So, and also it based on the functions, operation, perturbation, construction strategy, local search strategies, metaheuristic, convert to JSON. So, it has a solution, call it as a fitness of g of x, feasibility, permutation and frequency, and this will convert to JSON. So, this is a flow chart. You have to understand how the the problem is designing and what all the generic solver components are required. So, the solution class holds the solution vector x and the frequency vector f. It also contains the fitness g of x of the solution vector x and the information about whether the solution is feasible or not. So, additionally, it has a function that exports the solution to JSON. So, the most important class in the generic optimizer, it is optimization engine that works without the knowledge of the underlying the problem with the exception of the information. So, that is provided through the instance class, that is number of nodes, cardinality of E and the vector lower bound, upper bound. It contains 5 main groups of function. These are perturbation, construction strategies, local strategies and metaheuristics. So, the operators from the basis of the optimization engine, they perform the search in a given neighborhood and return the solution x with the best fitness g of x inside the neighborhood. In the scope of this thesis or this topic, neighborhood nk of x is defined as follows.